In this video, we're going to talk about factorials and permutations. So let's start with an example. Suppose that 5 people are running a race. Assuming that ties are impossible, in how many orders can these people finish the race? So here we've got a list of length 5, and the pieces of the list are, who comes in first place, who comes in second, etc. Because ties are impossible, that means that there's not going to be any repeated elements. Somebody can't be in both first and second place. So how many choices do we have for first place? Well, there's 5 people who could come in first. There are 4 people who could come in second, and so on. This is and. There are 5 people who could come in first and 4 people who would come in second and etc. So that means we should use the multiplication rule because we're talking about ands. So our answer here is 5 times 4 times 3 times 2 times 1, which is 120. And it's actually fairly common that we want to write something of this form, an integer multiplied by each positive integer less than it. This is equal to 5 factorial. So that's an exclamation point, 5 factorial, factorial. So it's read out loud as 5 factorial. And for any integer n greater than 1, n factorial is n times n minus 1 times n minus 2, all the way down to 1, the product of all positive integers less than or equal to n. And this is also the number of non-repetitive lists of length n made from n elements. So for example, 3 factorial is 3 times 2 times 1, and that is 6. 1 factorial is just 1, and 0 factorial is defined to be 1. So 0 factorial is 1. That might seem strange. The reason that that's the case is that 1 is the multiplicative identity. So if you multiply something by nothing, you're sort of getting 1, just in the same way that if you did like 3 over 6 and you reduce that fraction, you get 1/2. You don't get 0 over 2, you get 1 over 2 when you reduce that fraction. Okay, so let's use this to think about the number of ways to select k objects from n objects where we can't repeat elements. So here's a problem. We've done ones like this before. A club with 20 members will select a president, a vice president, a secretary, and a treasurer. If no one person can hold more than one office, in how many ways can these roles be filled? So like I said, we've sort of done things like this before. So both try to answer this question as we would have before, but also think, can you write your solution in terms of n equal 20 and k equal 4 using factorials? So thinking about the number of ways to select k objects, in this case 4 objects, from n objects, in this case 20 objects, where we can't repeat the elements. So think about that for a moment and we'll talk about it together. Okay, so one way that we could answer this question, as we did before, would be to say, okay, this is a list of length 4 with no repeats, because nobody can hold more than one position. And so, we've got our president, our VP, etc. And there are 20 possibilities for the first choice, and 19 for the next, and etc. So that tells us that we're going to use the multiplication rule because it's and between these. So that's 20 times 19 times 18 times 17. And we could, of course, simplify that if we wish. But we also said, okay, can we think about this using factorials? So this was our old ways of solving that problem. Could we also think about that using factorials? Well, we could think of that as 20 factorial divided by 16 factorial, because when we do 20 factorial divided by 16 factorial, that is 20 times 19 times 18 times 17 times 16 times 15 times blah 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 down to 1 over 16 factorial, 16 times 15 times 14 times down to 1. And then what happens there? Well, this part and this part cancel. The 16 factorial cancels with a whole lot of the 20 factorial, and so it is the case that this reduces back to just that. Why does this make sense logically? Well, we have 20 objects, but we only want 4 of them. So, if we normally think of 20 factorial as the number of ways to arrange 20 objects, we don't want to arrange 16 of them. So we only want 4 of them, not the remaining 16. So we're sort of dividing out by the number of ways to rearrange the remaining 16 objects that we're not interested in. Now let's think about that in terms of our n and our k. So the 20 factorial on top is pretty clearly our n factorial. What about our 16 factorial on the bottom? So our 16 factorial, that is 20 minus 4 factorial. In other words, this is n factorial over n minus k factorial. We have n objects in total. We want to arrange k of the objects. This n minus k objects basically not to arrange. There are n minus k objects that we're not interested in arranging out of the n objects. So that's where that formula comes from, and in general, this is the formula n permute k, the number of ways to select k objects from n objects with no repetition where the order matters. So this is called a k permutation, or just a permutation of n elements, and it's a non-repetitive list of length k made from n elements. I'm going to repeat myself just because it's important. N permute k, denoted this way and pronounced out loud like this, is the number of ways to select k objects from n objects where order matters. Is this person the president or the vice president or the secretary? And repetition is not allowed. Somebody can't be both. And again, that formula, n permute k, is n factorial over n minus k factorial. Why is it of that form? Well, as we saw above, we've got n times n minus 1 times n minus 2 all the way down to 1. That's n factorial. On the bottom, that's n minus k factorial is n minus k times n minus k minus 1 times ... all the way down to 1. This n minus k factorial cancels out with much of the n factorial to leave us with n times n minus 1 times n minus 2 ... down to n minus k plus 1. Just like up top, we were left with 20 times 19 times 18 times 17, where 17 is 20 minus 4 plus 1. I'd like to highlight here that what we can get with this formula is the same thing that we get using the multiplication rule. So we didn't really learn anything new here besides a new formula and this factorial symbol. And so I want you to keep thinking about the multiplication principle. Don't just memorize the formula without the logic behind it. Because with counting technique problems, the hard part is like knowing which technique to use. If somebody just says, okay, what's 40 permute 3, that's not the hard part. But the hard part is saying, okay, I'm looking at this application. Should I be using just the plain old multiplication rule? Should I be using combinations, which we'll learn later? Should I be using the addition and subtraction principle, etc.? So the hard part is knowing what to use where. So memorizing the formula is something, but understanding the logic behind it is really the important piece.